Hello everyone and welcome to lecture number 10. In the last lecture we have discussed about the block wall or blotch wall, right? And we have derived some of the equations for it. Now today we are going to see another topic of our unit that is important and we have already discussed about that. Today we will start antiferromagnetism. We will see the topic related to antiferromagnetism, that what antiferromagnetism it is. We will see antiferromagnetism. Today we will see antiferromagnetism, right? In the initial lectures we have discussed about the antiferromagnetism, that if an atom or if a material is having the orientation of magnetic dipole moments in such a way that equal number of dipoles are in opposite direction, then if one is in the upward direction, another will be definitely in the downward direction. Similarly, if another one is in the upward, another one will be in the downward. So the net magnetic moment will be zero. This kind of material in a same material, if it is there, this kind of arrangement is there, then it is antiferromagnetism, right? Then it is antiferromagnetic material, right? Now this happens, remember, this happens for small distance or separation between the interacting dipoles. The interacting dipoles. So antiferromagnetism results when you have a small distance between the interacting dipoles, means the atomic distance, this is A and this is B, this is atom A and atom B. If the distance between these two atoms, right, the distance between, if the atomic distance is small, right, then you will have this kind of arrangement. You will have antiferromagnetism for small separation between the interacting dipoles, right? This is atomic dipoles, right? Then the dipoles will try or will have a tendency for antiparallel alignment by the action of exchange forces. So this is going to happen, this kind of arrangement is going to happen by the action of exchange forces, right? And this behavior occurs below critical temperature. This occurs below critical temperature. This occurs below critical temperature, which is known as Tn, that is nothing but Néel temperature. Right? That is nothing but Néel temperature. This kind of arrangement occurs only below certain temperature, right? Only below certain temperature. If you rise the temperature, if you increase the temperature, then this kind of arrangement will not be there. This kind of arrangement will be disturbed and it may go to ferromagnetism, and by increasing more temperature it may go to paramagnetism, right? So this is with respect to Tn. If the temperature is below or lower than critical temperature, that is Néel temperature, then and then only you will have this kind of antiferromagnetism. You will have this kind of anti-ferromagnetism, right? Now to understand this anti-ferromagnetism, let us take an example of an atom A and atom B in a simple cubic structure, and let us understand that how it's going to behave, right? Now, consider a crystal containing two types of atoms, that is atom A and atom B. Both are having opposite spins. Right? So let us draw a cubical structure. Let us draw a cube over here. Let us draw a cube over here. This is a cube. Let us say over here, this is one atom, this is another atom, this is the another atom, this is another atom, this is also another atom. All corners are having same kind of atoms. Right? All corners are having, let us say atom A. I am using the same color and for A because all are having same kind of spin. All are having same kind of magnetic dipole arrangement, magnetic dipole direction. And we will also see that in which direction it is there. Right? And we will also try to have in between right? So this is also A. Now A is having a magnetic dipole moment in the direction upward. This is the direction of the dipole. Right? Now let us assume that we have a B atom that is existing in the center. I am using another color to differentiate. This is B. That is having its net magnetic dipole moment in the downward direction. That is having a net magnetic dipole moment in the downward direction. Right? You can assume a similar kind of structure on the right hand side. You can assume similar kind of structure on the left hand side. You can assume similar kind of square on the bottom, on the top, on the right, left, everywhere, because the material will be made up of a bulk material. If you see the bulk material, you will see number of these kind of cubes will be attached to each other, right? Number of this kind of cubes will be attaching to each other. In that you will also have, you can also visualize that this A atom, in that case you can also visualize that this A atom is being surrounded by number of B atoms. You can see that number of B atoms will be surrounded if you assume more cubes over here, and over here. In this cube, we can only see or only visualize that B atom is being surrounded by A, but in bulk, this A individual, all A's will be surrounded by B and vice versa. Right? So this is the basic structure to understand ferromagnetism, anti-ferromagnetism. Right? Now moving ahead, we have assumed that we have two types of atom. Atom A is having direction in the upward direction, that is magnetic moment in the upward direction. B is having opposite magnetic moment, that is in the downward direction. Now, at very low temperature, this interaction is effective. At low temperature, the interaction is effective. At low temperature, the interaction is very effective, and as the temperature is rise, then the efficiency of the interaction decreases and susceptibility increases. Efficiency decreases and susceptibility increases. For that, let us see another graph of temperature versus susceptibility. This is the graph for antiferromagnetism, for susceptibility versus temperature. You will find that it's having this kind of curve. You will find it's this kind of curve. Little bit of more unsharp over here. It's my mistake, right? So, right over here, this is the Néel temperature. This is the Néel temperature point. This is T of N. This is T of N. Right? In this area, in this part of temperature region, the material will behave as antiferromagnetism. Material will have antiferromagnetism. As the temperature is low, the interaction is effective. As temperature increases, as we increase the temperature, the efficiency of interaction decreases and susceptibility increases. Right? You see, susceptibility is increasing. This point. Understand the statement. As T is increased, then as T increases, let me write the whole sentence. Then efficiency of interaction decreases and chi increases. Finally, at T of N, which the spins are free, and above spins are free and material becomes paramagnetism. Right? After that, material becomes paramagnetism. Now let us understand this, that what it wants to say. It wants to say that as low temperature the interaction is effective. You can see this part, you can see this part. Remember, over here you will have two type of interactions. That is AA interaction and AB or BA or BB type of interactions. You will have this kind of interactions. You will either have A or A, you will either have B or B, you can either have AB or BA. So that is nothing but the interaction between two magnetic dipoles. Right? As the temperature is low, the interaction is very effective. And you can see that it's having antiferromagnetism. Right? As you increase the temperature from this point, remember, this point is not zero. This is not zero temperature. Remember this point. As you increase the temperature, susceptibility increases because of the increasing more, right, the spins, more freeness of the dipoles. Finally, at this point, that is nothing but the Néel temperature. The temperature is nothing but the thermal energy. It is very much high at this point. It is sufficient to break down the interaction between these two dipoles. It is enough to break down the interaction between these two dipoles, and it will lose their orientations. This dipole and this dipole, they will lose their orientation, and it may happen that this can go to this direction or this can go to this direction. So you will find to see decrease in the susceptibility. susceptibility, right? You will find to see decrease in the susceptibility, and at some point it will become paramagnetism. It will become paramagnetism. Now we want to find out the relation between this chi. We want to find out the relation between this chi, this Tn and T. We want to find out the relation between chi, Tn and T. So in that case, we will have two cases. That is, if T is greater than Tn and T less than Tn and T less than Tn. So let us start our derivation considering these cases, right? So starting our derivation, let there be two subnucleus A and B, and besides an antiferromagnetic, and we have AB interaction. We will also have AA and BB interaction. Now, the molecular field of AB, let the molecular field at A and B are H of A and H of B. This H of A and H of B. Then we can write H of A will be equals to H minus alpha M of A minus beta M of B. And similarly, for HB is equals to H minus beta M of A minus alpha M of B. Over here, this H is nothing but applied field. This H is applied field. H is nothing but applied field. Ma and Mb are respective magnetization. Ma and Mb are respective magnetizations for A and B, while alpha is interaction parameter for two atoms having alpha is the interaction parameter. Alpha and beta actually both are the interaction parameters, but alpha is for like spin, that is AA or BB, while beta is interaction for two unlike atoms. Right? Beta is nothing but the interaction for two unlike atoms, right? Now let us start our case, and we'll take the first case. We will take the first case, case 1, that is, we have T is greater than Tn. T is greater than Tn. When the temperature is above the Néel temperature, we are far away from saturation. When this is nothing but the temperature is above greater than the Néel temperature. when the temperature is above knee temperature, we are far away from saturation, and in that case the magnetization of lattice A is given by magnetization of A is given by capital M of A is equals to capital N Pm square by 3 K dt H of A. H of A. Right? Over here N is nothing but the number of atoms, T is temperature, H is nothing but the field, and P is given by where Pm square is nothing but 2 equals to mu b square g square. Mu b square is nothing but Boltzmann's constant, g square is nothing but Landau's g factor, that is gyration ratio, and j into j plus 1. J is nothing but angular momentum, right? And j plus 1 is responding the Brillouin zones, right? Similarly, we will have for M of B is equals to N mu square by 3K T, that is H of B. This is equation number 2. This is equation number 1. Now, moving ahead, we have M is equals to M of A plus M of B is equals to, now substituting the value of MA and MB in this above equation, we will get N Pm of square by 3 Kb of T 2H minus alpha plus beta into capital M right? Now this is equals to M, right? From where do these terms are coming? This alpha beta, I have substituted the value of HA, substituting the value of HA and HB from the previous equation, right, into this. From there we are taking common, this part is common, that H part is going to have 2H and alpha plus beta is going to have M, right? This is some of the internal steps which I feel that you can go through by yourself. Now this is I have obtained directly by solving some of the steps. Moving ahead, what we will do is we will multiply this term with both of this, and we will take this part on the another side. Another side. So we will have n into 1 plus n Pm square 3k dt into alpha plus beta is equals to 2n P of subscript m square k of t dot h. Remember, I am just multiplying this term with this and this. So I will get this term is this one, and this multiplied by this has been taken on the another side, and I have taken m common. This m and m will be common, right? Now we know that m by h is nothing but chi. We know m by h is equals to chi. So chi can be written over here instead of this. But before going to chi, let us assume some of the things. That is, now let over here we have c dash is equals to 2n square by 3k of bt. This is this t will not come. This is nothing but c dash. We are assuming it, and t of p is equals to n of square 3k b alpha plus beta. So this term we are going to recognize as t of p, not t, and this term we are going to recognize as c dash, Now moving ahead, I will have m by h into 1 plus tp by t is equals to c by t. This is what we will get after substituting c dash and dt in the previous equation. This m by h is nothing but chi into 1 plus tp by t is equals to c by t. This tp by will be going to over the another side. This t will be cancelled. This t and this t will be cancelled. So chi is equals to c dash by t plus t of p. This is what we have obtained the relation between the susceptibility and the Néel temperature, right? Temperature T and T of P, that is paramagnetic temperature. This is the temperature T, this is the temperature T greater than Néel temperature. This is the case where we have taken T is greater than T of N. We have taken T is equals to greater than T of N, right? Now let us take another example where we have T less than T of N. That is case number 2, where we have T less than T of N. At Néel temperature, Tn itself, T of N itself, we are considering at Néel temperature itself, we are still far away from saturation. This is our assumption, or this is our situation. Thus, in absence of applied magnetic field, we may write T is equals to T of n, T is equals to T of n, and we will have equation of ma is equals to minus of n pm square by 3 b of t, and remember this n into alpha m of a plus beta m of b. This is we have obtained from the previous equation of magnetization, that is magnetization associated to lattice A. This is nothing but magnetization associated with lattice A. In the previous form, the equation number 1, we are having h of A. Substituting this value of h of A instead of in this equation, we will get this kind of form. We will get this kind of form, right? Because in h of A, h will be equals to 0. So minus alpha m of A minus beta m, this minus sign is coming from h, right? H of A. So this is equation number 4. Let us give this is equation number 4. And similarly we will have the equation for m of b. But before going to that, let us have the solution of the above, that is 1 plus multiplying this individual terms, this term, and this term, and taking this part on the other side, we will get 1 plus n of square 3k b of t n alpha m of a is equals to plus n m of square e k t beta m of b is equals to 0. Similarly, we will have another equation for m of b. Right? Similarly, for m of b is equals to, we will have another equation, that is n m of square by 3 kb of t beta n of a, this is n m of a, this is m of a, remember this is m of a, plus 1 plus n square by 3 kbt of n alpha m of b is equals to 0. This is equation number 6. This is, let us say, 5. Now, on comparing equation number 5 and 6, we will get simultaneous equation. We will have simultaneous equation. So the solution of simultaneous equation will have equation 5 and 6 for one solution. Equation 5 and 6 are simultaneous same equation. Solution of simultaneous equation is m of A is equals to m of B is equals to 0. Now spontaneous magnetization will take place if there exists a solution for simultaneous equation. So for finite value of m of A and m of B, we will take determinants. That is in the form of two equation. We will have determinants that will be in the form of determinants, and also substitute C dash. We are also substituting the value of C dash. Remember, C dash is nothing but 2. C dash is nothing but 2 and T of m square by 3 k beta t. Right? Substituting that value, we will have 1 plus C dash by 2 T of n alpha. Remember, in C dash we have only taken n Pm by 2, Pm by 3. 2 was there, but it is not written. 2 is not multiplied. 2 is not multiplied over here. So we are dividing this 2. We are dividing 2 because C dash we have not considered 2. That factor was not there. Right? You can see the value of C dash. If you will see the value of C dash and compare, then it will be more clear. Now this will be C dash by 2 T of n. That will be beta is equals to 0. This is from equation number 5. Now I will be having equation from equation number 6, that is C dash by 2 T of n dot beta. That is the first term. Now I will have second term. That is 1 plus C dash, 1 plus C dash divided by 2 T of n alpha. Right? This is nothing but the determinants of two equations. Now going ahead, we will derive the determinant form. We will multiply this two term and multiply this two term for the solution. We will get is we will get 1 plus C dash by 2 T of n whole square is equals to C dash by 2 T of n beta whole square. Now whole square will cancel, so we will have 1 plus C dash by 2 T of n alpha is equals to C dash by 2 T of n beta. Square will going to cancel out each other, right? Now moving ahead, we will find out the solution to 1 plus n, that is taking this part on this side. We will have alpha minus beta is equals to 0. Therefore C dash by 2T of n, that is alpha minus beta is equals to -1. Now changing the sign of this alpha and beta, we will change -1 to +1. So beta minus alpha is equals to +1. We have changed the minus sign. If we take this one on the other side, we will have -1. Again, if we change this beta alpha position, then we will have -1 over here. Minus will be plus, we will have +1. Right? So finally, we'll derive the value of Tn. We will see the value of Tn, that is T of n. This T of n will be equals to C dash beta minus alpha divided by 2. Now what does the significance of this beta and alpha in defining the value of Tn? What is the significance of beta and alpha in deciding the value of Tn? Tn is nothing but the value of Néel temperature, right? Tn is nothing but the value of Néel temperature. The importance of it is from the above equation it is clear that the Néel temperature increases as AB interaction that is beta, if the AB interaction increases, is stronger Néel temperature increases as beta is stronger. If beta is stronger, you will have a whole value will be high. So Néel temperature increases. And if you have whereas its value decreases with AA or BB, that is alpha interaction. When the similar kind of atom interaction increases, the value of Tn is going to be less. It will decrease. When you will have different kind of interaction, strong interaction, then you will have higher the value of Néel temperature. So this is the relation of the interaction between let us atom A and atom B having opposite magnetic dipole moment, and the relation between Tn. This Tn value will decide up to which temperature the material will behave as an antiferromagnetic material. It will have antiferromagnetic properties, right? So this was all about antiferromagnetic material and its derivation with respect to the change in temperature, right? Okay.